12. You guys have any question about midterm? Okay. So let's move to chapter 12. So it's about ceramics. I believe we studied a little bit about ceramics in the first chapters, chapter 2 or 3. But here we're gonna just look into ceramics a little bit more. So ceramics are basically, we have at least two elements, and the atomic bonds are mostly ionic or covalent. But it could be just a combination of these two types. It depends on the electronic activities of those atoms. But just to determine the crystal structure of our ceramic, there are a few factors we have to look into. First is the size of ions. So basically, most of anions are much larger than cations, right? That's the first factor. And in order to have like a stable structure, they should be in direct contact, like touching. For example, in the first figure, it is unstable because the cation is not touching anion. The second thing we have to be careful about is the charge of the overall structure. We know in total, the general structure should be neutral. So based on these, we have some concepts here. First concept is coordination number, which is basically the number of anions that are like the neighbor of cation. For example, in the figures here, the second row, you can see the coordination number is 3 because in the middle, that black dot is our cation, which has like 3 neighbors anions. Or in the first row, the coordination number is 2. There is another important thing, which is the ratio of the radius of cation to radius of anion. And that ratio can tell us a lot of things. Actually, this table here is showing the relationship between the structure, coordination number, and that ratio. So basically, if that ratio is very small, below 0.155, you're going to have like a linear structure in which the coordination number is 2. But if it lies down between like 0.225 to 0.414, it's going to have like a tetrahedral structure in which you can see the cation is at the center of this structure, which means it has like 4 neighboring anions. So, based on these things, let's move to the first question. On the basis of ionic charge and ionic product given in the table below, predict the coordination number and crystal structure of the following materials. So it's pretty simple, right? We go back to that table, it means we just have to find this ratio. The ratio of the cation radius to anion radius. And we'll have the table here. ratio and finally the structure based on the coordination number, which we get from the table that we just saw previous slide. Any question on this one? So this one is more challenging. So first thing I have to mention is, well, this table here is purely just based on geometry. In reality, there are some ceramics that do not follow this table. They can have like a ratio at the range of coordination number 4 in tetrahedral, but they have a different structure. But here, for this chapter, we are not interested in those ceramics. So we're gonna just stick to this table, and just based on geometry, we want to calculate the angle between the bonds of a tetrahedral structure. In tetrahedral, it is basically like the structure we just saw here, this one, with the purple. So if you look at this thing, this structure here, I put a figure so it would be easier for you just to visualize it, and it already has that. So when it says we want to find angle between the pole and pole, we are looking for this angle, right? Which is like equal to this one or this one. So it's basically like 2, 5. Actually, just pure geometry. But since you will have this question in your homework, that's why I just included this here. And this term is 1. Basically, 1 is square root of 2 times a. Oh, I'm sorry, this is 2y, because y is like half of that length. So 2y is equal to this, so y is going to be this. So far we found theta, and so the rest of the solution is very easy, right? Because so, in that triangle there we equal to 4 and just the add between these bonds here, 1 5 here, and 5 here. So just takes a little bit of geometry. Any questions on this one? Everything clear? And you have a similar question in your homework. So next thing we want to talk about, again, on the crystal structure of ceramics. So most of the ceramics have like equal numbers of cations and anions, which we show them with AX compounds, in which A is denoting cation, X is denoting anion. For example, on the figure on the right is like the general structure of AX crystal structures or ceramics, but the most famous of those structures are shown here. So this one is the rock salt structure, which is the structure of salt, sodium chloride. This one is another famous structure of this type of ceramics, cesium chloride, and this one is showing zinc sulfur like this. But anyway, it's just some basic definitions. But we can have like different numbers of cations and anions in our structure, in which we show them as this one here, AMXP, which M and P are showing like here, for example, which have like cesium. Oh, this is not cesium, whatever it is, oxide. So also we can have more than one type of cation, which we show them like this one here. So we basically add another letter, which is B, shown in general with B. Yeah, so you don't have any question about like this specific slide, but I just wanted to show you, just go over some basic definition. The next thing is the density of ceramics. So how do we calculate the density of ceramics? Well, this is the formula we use, in which these are, in the parentheses, is the sum of the atomic weights of all elements, all cations and all anions. And N prime is showing the number of formula in a unit cell. I'll tell you what that means. Finally, we have Avogadro's number and the volume of the unit cell. Okay, so let's see one example of this. It says calculate the density of iron oxide given that it has this rock salt crystal structure. So I just show you the rock salt and it's here. And given the radius of both iron oxygen and also the atomic weight of both elements. So you can try to solve it. So we're gonna use this formula, right? But let's talk about this n prime first here. So number of formula units in a unit cell. So our formula is FeO. So it has just one iron and one oxygen, right? But in a unit cell, which is shown in this figure, how many oxygen, for example, you have? And oxygen is the anion, right? So it should be the bigger or the green elements here. But how many do we have here? So each one of these green elements on the surface of our unit cell, just half of it is inside the unit cell and half of it is outside the unit cell. So in total, we have 6 of these oxygens, so it's going to be 3 in total. What about those at the corner? So in total, we have 8 of these types of oxygen, but together, we only have one total oxygen inside the cube, right? Because each one of those, only 1/8 of
About the
each
same,
element
actually. I feel the same.
is inside that unit cell. Does that make sense? So basically, it's something like just half of 6 elements.
I think you got this. Even though the grades are bad, honestly, if you really like this major, I think if you just get through the schooling part, because like learning things like
And
engineering
it's
constantly.
the same for
It's
the
just
red
the school
elements,
part, that's right.
which
I
is
understand the
every in
basics
this
of
question.
So, I mean, honestly, you just have to pass the class. I feel like if I get another
So
goal,
if
like
you-
hopefully keep that to graduation, that is my only goal at this point. I gave up on the other stuff.
If you think about it,
Get an internship.
each one of these,
Early, yeah. You know, because
so
you'll have a
we
team.
have one in the
grow
center, which is
together,
totally inside
you know,
our
do you just
structure.
think you're not
So
making
we're
it?
gonna
Like,
count
because,
on
I mean, look, if you think about
what
it,
about
after you get
these
this
that
and
are
mechanics and stuff,
located
it doesn't
on
get
the
any
edges of
harder.
this
It's the same things,
So-
but like in different ways. Like even
For each
like
one of these,
fluid-
only
fluid
one,
basic
like
fluids is like
25% of
hydraulics, but
these
like hydraulics
elements
is
are
more
inside
advanced,
our
more
unit
systems
structure,
and things.
right?
So like literally after we get to the next set of classes,
have here
it's just a sophomore year class. As soon as you get through, it's gonna be the same thing over and over again.
This makes
Five,
sense.
six, seven,
Oh,
eight.
this is your second. Oh, I didn't know that.
So
Yeah, this is gonna be. I can use that
Oh.
myself. Because his grade that's too big. Literally, if you can get yourself 50 something on the test and a curve, get you to a
So,
something that can
the
get you a
bottom
C
line
right
is,
there.
and in that formula, it's gonna be
It's either wait a
equal
little
to
bit
40.
or wait it. If I waited too late, it might hurt my GPA, so it's one thing.
Right.
I'll just say maybe
Way
two.
too late to get out, like, or even drop class. That's fair.
It's not till tomorrow, but I don't know what time, so I gotta figure out later
I
today.
gotta figure out something. At least with this class, we got to the second test. I remember in previous classes, I never get to the second test. I had to decide to drop it after one test. You know, yeah. I get that though. Yeah, you have to weigh your best options.
Yep. But
That's true. You have to keep a certain GPA before classes. Cool.
I just hope your test is good.
Okay, now we figure out N.
Like I said, that is literally, I'm just doing what I just told
So
you.
we said
If
it's
I can
gonna
see
be
on this test and get an 8 on the next
N
test, I
prime,
don't,
which is 4
because they,
times
I'm really just gonna go hard for that last thing.
the sum of atomic weights.
That's literally my test, because it's not that I completely stuck on it.
Over the
And I was
volume
like,
cell.
I'm gonna get the,
So what is
let's try
the volume
I mean, it's
of this structure here?
Okay, all the, hopefully it's also the zeros, because there's so many things. I was like, okay.
Let's think
Then the second
about
question,
the
I wish I had more
volume
time to
of
spend on
our
that
cell.
one, because I definitely
So
missed out on
this is a
certain
cube. So if we have, like, for
and almost
example,
didn't even know
length
to do for
of
long runs on that one.
the length of our cube,
It's because there was so many
pretty clear
equations.
that
I even
volume
know
is
my
going to
calculator.
be
I was like, am I doing
right?
this equation right? So I
So
just
we
don't
have
think I
to
got the right answer
find
out.
A in terms of the radius of FE and O.
I appreciate that.
If you look at, for example,
I was aiming to
only
get like a 70 on my number.
one
I get
edge,
above a 50,
so
and the curve gets me to a 60.
in reality,
I'll take it.
these elements
Just make
are
it
touching each other, right?
Honestly, like you said,
So you have
you do
one.
even one question, I will take it.
I still want to be engineering, but if it's not this engineering, I'll try to
What
fix
do
it.
we here
Engineering, you're saying.
for this element?
Oh, that's why you're in the harder one.
You have
So you know
R
that
over
completely.
here,
C
another
plus.
R over
Or C
here.
plus, which is a B because there's only A, B, C
These
goes
are
by those letters.
oxygen,
You have
because
C
that's
Oh, yeah, I realized that for all the engineering, that's why I never even thought of them anymore. Because I realized how hard it was for me. I went straight to civil. Because C minus is any course you want to get
is
above C
equal
minus.
to
So,
I'll
3
just
times
say I make sure.
R
no, that's
E
you got this.
times R O.
Regardless of what happens, I'm still going like.
Does that make sense?
I got you.
Yeah, I still got you guys to
You
make
guys-
videos every day because I know you need
We should
them.
keep it
I
down,
appreciate it.
guys. We should keep it down. Thank you.
Sorry.
Okay. So that's our A.
Okay.
So basically we're gonna have, and also we have the radius, right? What's the ionic radius here? For Fe is gonna be 0.0077 plus 40 times 3, and also the electric.
You can say that if you want to.
Just have to be careful with the unit conversion because this is nanometer, right? But we have to change it into centimeter to get the final answer in terms of a gram per centimeter. Okay, any question on this one? Okay, so I guess we have to go okay, the next topic is about silicate ceramics, right? So silicate ceramics is basically just different type of structures that we can have from silicon and oxygen, and we can have like several structures. One of the most common one is just this SiO4, which has a negative charge of 4. You can also have, for example, Si2O7 or some other types. But two famous material we have from the combination of silicon and oxygen is quartz and glass. Glass is basically just non-crystalline silica while quartz is a crystal example. These are again just the basic definition that they were in the slides, so I just want to quickly review. I don't think you have like a special questions for this. So we want to have implications astrology. And I want to specifically talk about like point defects. And we learned about point defects before, which we can divide them into two different categories: vacancies and interstitial defects. Vacancies is basically when one atom is not present as it's supposed to be. But interstitial is when it is in the wrong position inside our lattice. In terms of ceramics, we have Frankel defects and Schottky defects. So, Frankel defects is when we have a cation in a vacancy and a cation in an interstitial position, and it's like a pair defects. Why do we have pair here? Because we are talking about charged elements. So we cannot have like, in total, the charge should be neutral. That's why we have pair. For example, we have a cation vacancy. It means a missing positive charge. So somewhere else we should have like an additional positive charge in terms of interstitial, cation interstitial defects. So that pairs together called Frankel defect. Another type of defect in ceramics are Schottky defects. And here we have both cation and anion vacancies. And that's how we balance the charge in total. So both the negative charge and the positive charge are missing. So you might ask why there is not like a third type of defects, because interstitial defects are only for cations. You cannot have like an anion interstitial, because anions are very large, and if you cannot like this one, you cannot add one of these 4 and 5 somewhere in the lattice, because they're going to put a lot of strain in the lattice. So there is no interstitial anion. Interstitial is only for cation. So how do we calculate or determine how much defects we have in our network? So you are familiar with this type of formula that I've said before, and it's basically the same. We use the same method. So to find out how many Frankel defects we have in our network is total number of lattice size times this exponential of Q is again like the energy or activation energy for this type of defect, Frankel defect, over 2 times Boltzmann's constant and temperature. And it's the same for the Schottky. And the Schottky has like its own special activation energy. So, based on these two formulas, let's look at this example. It says calculate the number of Frankel defects per cubic meter in a zinc oxide at that temperature. The energy for the defects formation is given. Also, we are given the density of the zinc oxide at that temperature. So I put a hint for this question because this formula here is for, I think, chapter 4, so it's for midterm 1. But it's just good for review, and we can use it here to find n, and from that we can find the number of defects. Okay, so I think it's almost clear. I have the calculation, I just plug in the numbers. First, I calculated the total, that is 6, and just something you have to be careful about is this unit conversion here. Since we have like the density as gram per centimeter cube, I have to convert it in meter because I want the final answer to be per meter cube. And the rest is just plugging in the numbers given in the question in the formula. In addition to this one, okay, so almost this chapter is one more question. So the last thing we want to talk about is the mechanical behavior of ceramics. Actually, we just want to focus on flexural strengths of the ceramics. Why? Because we cannot do the tensile test on ceramics. They are so fragile, actually, so brittle. So it's not practical to perform tensile tests in ceramics. Instead, they use like a bending test. And based on that, they can measure the flexural strength of the ceramic. So, in this type of test, we have, well, we usually use a three-point bending test, in which we have 2 point and 1 point for applying the force. And our sample is usually like a rod with circular or rectangular cross section. So in this type of test, the most compression is going to be where we just apply the force. And similarly, the most tension happens here, at the bottom surface, where we apply the force. So to measure the flexural strengths, these are the formulas. This one is for rectangular cross section, and the bottom one is for circular cross section. And like for rectangular, just be careful with B and D, which D is like the height of the rectangle, and B is the width, and D is the height. But it's usually confusing, so I think in most of questions we're gonna specify what is D and what is B, because it's gonna change your answer. Let's solve this question. So, a 3-point bending test was performed on aluminum oxide specimen having a circular cross section. That would need to be loaded by the BNP of radius 3.5 The specimen fractured at a load of 950 Newton, where the distance between the support points was 50 mm. Another test is to be performed on the same specimen, a specimen with the same material, but with a different cross section. It has a square cross section of 12 millimeter length on each edge. At what load would you expect this specimen to fracture if the support point separation is 40 mm? Do you guys have any idea how to solve this problem? Well, we are given like a first test in which we know the specimen fails at like a specific force, which is 950 Newton. Right? And we are given a different condition, a different test, same material, and it's the same material, so it has like the same properties, right? Same material, different test, different cross section, and we are asked to find at what load this material is going to fail. just talked about flexural strength, right? So if we know the flexural strength, it's the strength is the point that the material begins to fail, right? So it's asking, it's not asking for that, but I mean, if we find the strengths, flexural strengths, we can find the answer, right? We can answer the question. Let's solve it together. So let's focus on the first condition in which we have a circular cross section. So we can find the flexural strengths to show you this from the first test, because actually we have everything. We are given the force, we are given the length, which is distance between support points, and we are given the radius. So plugging those numbers for the first test, force was 950. We had a distance of 50 millimeters, so we convert that into meter. And radius is 3.5, again millimeter, which we need to convert it into meter. And we get our strength as 352 megapascal. Now we want to apply it in the second test. In the second test, we have a square cross section. And for a square cross section, what was the formula? It was different. So here, since it is square, B and D are going to be equal to the given lengths, which was 12 millimeters. So it's 12 millimeter, 12 times 10 minus 3 meter. Okay, we can write down the same thing actually. So distance is going to be equal to, look at this formula here, 3 F times L over 2 E times D squared. So since B and D are equal, we can write it down as this. So here, we know the strengths. We calculated from the first test. We know the L, the length we are given is 40 millimeter. We know the D, which is the dimension of the square. And we are looking for the force. Now it looks simple, right? So if you just change the order of this equation, we get calculated from the first test, 12 millimeter, Q, and finally the length is 40 which means final force is equal to this. Does that make sense? Any questions? Okay. So go over to the next chapter. Okay, so I'm gonna go over chapter 13 with you guys. So I guess one of the first sections that they mentioned in, I guess for your homework in chapter 13 was refractories. Obviously, the properties of basically ceramic materials or like brick type materials. So in this chapter, they basically talked about the stability of these refractory materials to withstand really high temperatures without melting or decomposing, and they remain unreactive and inert in harsh temperatures like hot, corrosive environments. And they also have a really good ability to provide thermal insulation and support mechanical loads, as well as being resistant to thermal shock in some of these refractory materials. And you can see them in some applications like linings for furnaces and smelters. They will find like steel and aluminum, those like that. You see them a lot in furnaces or cement kilns, things like that, power generators. As well in this chapter, they mentioned that there's like two different types of composition, basically clay and non-clay. But in your homework, for your homework questions, they're mostly going over this stuff here, which is, again, more like phase diagram type stuff. So here in this chart, is there anything to mention? So I mean, so basically they mentioned the material type refractories, and they also mentioned the phase diagram for these refractory type materials. And for your homework questions, that's basically what they're kind of asking you for. So like for example, in this question, so they want you to find the maximum temperature to which the following two magnesia aluminum refractory materials may be heated before a liquid phase appears. So part A of the question is asking a spindle bonded aluminum material of composition 95% alumina, and then 5% of magnesium or magnesia. And then part B is asking, based on the previous thing that I was just reading, a magnesia alumina spindle of composition 65% of alumina and 35% of magnesium oxide. And a weird thing that they did with this one, so in your homework, they should give you like a little hyperlink to the figure itself, but they want you to look at figure 1223. So we're in chapter 13, but we have to go back in chapters so that we can find this thing. So I really annoyed, but it is what it is. So feel free to work on it. This is, so like these two questions definitely are basically like phase diagram stuff. So if you know your phase diagrams, this should be not too bad. I'm just gonna pull it up on my end to make sure I'm giving you guys the right stuff.
Okay, so for part A, so looking at the figure, if we take into account the 95 weight percent, which should be around right here. So basically, how far can we go before we hit a liquid phase? And so if we take this and we just travel up, my line is not very straight. So we hit, I guess, that boundary between the solid and liquid phase there at that point. And if we look over now at the temperature, we can draw a line here. And so based on our phase diagram, we can see that maximum temperature without a liquid phase corresponds to that temperature there of the eutectic isotherm on the aluminum side of the phase diagram, which is about 2000 degrees Celsius. So I guess we can write that here, just so that we know. And for, this is a different color for part B. So for part B in red, the maximum temperature without the formation of the liquid phase for the magnesia aluminum spindle at 65 weight percent, which is about this guy right here. So now if we go up, we hit that point, is that correct? So we'll see the phase boundary between the magnesium alumina, the SS, and magnesium alumina plus the liquid phase, which is this guy. So that's kind of sitting in these areas. 65, yeah. So just slightly to the left of the carbon melting point, that liquid phase. And so maybe my 65% is off. So technically with this one, the book is very specific with the value. But if you were to ask anyone else, so maybe where my line is originally a little bit off, I think they're talking about this point here, or maybe a little higher. But they're saying that that temperature should be about 2030 degrees Celsius, which I'm not too sure how they're able to get the extra 30 degrees Celsius in there, but oh, I see, never mind. So yeah, correct. Hold on 1 second. So take this out. Yeah, so about there. So we hit this phase here. That phase should still be solid, and then we go up just a little bit higher. So 2000 is like here, and then they're calling it 2030 degrees Celsius, but it's honestly very hard to tell. Any questions on this one? So yeah, kind of straightforward. This one's like chapter 9 stuff, basically. And then if we go here to this problem, it's saying we're asking for the magnesium or magnesia alumina system. So same figure again as like the last one. What is the max temperature that is possible without the formation of a liquid phase like at all? And at what composition or over what range of compositions will this maximum temperature be achieved? Okay, so looking at the chart, so the maximum temperature that we can see without the formation of a liquid phase at all is going to be approximately so basically way up here. So by the time it becomes a liquid, it'll basically have to go over that 2800 Celsius. If you go anywhere else across all this, obviously it's going to be much less. So essentially we just need a pure magnesia system for this question. So I guess to answer that second part of the question, it is just pure magnesia. And to answer the first part of that, it's just 2800 Celsius. And then just so we can see it visually, we just go all the way up that line. and we don't have to traverse across the table because our point is right there, and we're basically sitting on top of that 0% for that problem. Any questions on this one? Again, too, this was pretty easy, not too bad. I think there's another one like this one where it's just like basically you just read the graph and then you just write down the answer inside the y plus. So I didn't add that one in there. I thought that was a little too, I guess, straightforward. So the next section that they talk about here that I wanted to discuss with you guys was the fabrication and processing of glasses and glass ceramics. So essentially in this chapter they were mentioning how glassy or non-crystalline materials, they don't solidify the same way that crystalline materials do, and upon cooling, a glass can become more and more viscous in a continuous manner with decreasing temperature, and there's no definite temperature at which the liquid can transform into a solid, as like other crystalline materials do. But for glass materials, the volume is going to decrease continuously with temperature reduction, and so a slight decrease in slope of the curve occurs at what is called the glass transition temperature, which is the TG. They also call it the fictive temperature, but you can just call it glass transition temperature. And so they mentioned below this temperature, the material is going to be considered a glass underneath that TG temperature. And then above it, the material is going to be first supercooled. It's going to be a supercooled liquid, and then finally a liquid. And so here you can see like the phase diagram for basically a glass and its properties. What else did they mention? So they specifically also mentioned, and it was in your homework as well too, they talked about in that chapter, it's not here on the slide though, figure 13.14, where basically they're plotting, it's a logarithmic plot of the viscosity versus the temperature for a couple of different types of glasses. So we'll go over that a little bit more once we get to that question. And they also mentioned this here viscosity. So I think you guys also have a question on this. So essentially the viscosity is going to relate the shear stress to the velocity gradient. And here you can see the equation for it there. In your homework, they don't use tau, but they use sigma. So I think in that case, you just plug in your sigma value into this type of equation. Again, we'll see a little bit later once we scroll to it. So basically, that's kind of what they went over for this chapter. And slides everywhere. Okay, so for the first one, these are more like kind of like the more difficult like calculation-based questions that we felt that we should go over with you guys. Should I submit it? So in this problem, they want you to compute mass fractions. So again, this is like from maybe like chapter 10 or something like that, or maybe chapter 9 a little bit. Mass fractions and that good stuff. So they want you to compute the mass fractions for all of the refractory materials at 1600 degrees Celsius, listed below, all of those. In this chapter, they don't give you the equation, but essentially we're going to be following this equation here that I pulled from chapter 9. So again, yeah, so it was chapter 9. Okay. And you don't necessarily need this chart to help you solve it. They mentioned this chart to kind of help you visualize like the weight percentages and to kind of see where you are on the chart. so the problem wants us to compute the mass fractions for all of these at 1600 degrees Celsius. I guess just for us, we can say that's about over here. Not that we need it, but so if you want to visualize it, it's right there in black on that little graph. So for part A, we have 6 weight percent of the alumina and 94 weight percent of the silicon dioxide composition. So we have to use the Levermore expression, which is that one that I already circled down there. I feel like the form is correct. I just don't like the, so in this case, they're using like alpha or whatever in that one. But I'll write down, I guess, the correct one for you guys, so you guys can see it. So the composition of the original alloy subtracted from the composition of silicon dioxide, divided by the composition of, I believe they're saying that is the liquid phase, minus the composition of the SiO2. Oh, wait a minute. Yeah, so I guess you do need the phase diagram. I wonder if they actually give the hyperlink to the phase diagram in your homework. Okay, so to figure out the mass fraction at that temperature for part A, we need to create a tie line across the SiO2 liquid phase at that temperature. So after you create your tie line, you should end up with the composition of the liquid phase should be about 7 weight percent of the aluminum. And the composition of the SiO2 should be 0 weight percent of, I said, I guess I'll write it out like this, saves these. And then as much as, so the composition of the original phase is going to be about 6 weight percent based on the figure. That's it, 2.3. So the mass fraction of the liquid using that Levermore is going to be it's going to be 6 minus 0 divided by 7 minus 0. So you'll end up with a mass fraction of 0.86 for part A, so I'll just put it here. So we can see it. And essentially, that's kind of what we're doing for the rest of these as well. But I'm going to walk you guys through those. So for part B, we have 10 weight percent this time of the alumina and 90 weight percent of the SiO2. I'm going to just write out the equation so we don't have to spend too much time actually do the calculation. Composition of the mullet original composition divided by composition of the mullet minus the composition of the phase. And so for the tie line constructed across the mullite SS liquid phase at 1600, you'll end up with a mullite composition of the mullite, which is about 72.8%, and the composition of the liquid phase, which is about 8%. And we know that the original composition of our alumina is going to be 10%. So if you do that math, you should end up with something that is 0.97 for part B. And so for part C, kind of the same story here. We're just going to be using, we're using this equation in part C. But we are going to use, because we know we have in part C 38% of the alumina. So it's going to change a little bit. So we're going to have mass fraction equal to 72%, which is the composition of the mullite at that 1600. Subtracted by the 38% in this case of the original composition, and that's going to be 72 minus 8 at the bottom. And that 88% is the composition of the liquid phase. So that's going to be 88% of the aluminum. So for part C, you should have 0.66 as your mass fraction. And then quickly we're going to do part B. And part D is a no-brainer. So for 88% of 88% of the alumina, 20% of the silicon dioxide composition at that temperature, only alumina and mullite phases are present, which means that our mass fraction or our W subscript L is going to be equal to 0 at that point. So if we go here, we go to the 88%. In that case, it's going to be 0. And if we do that, this should be 10. And this one was the 30, I believe. So I just want you guys to see all that. Okay, any questions on this one? Okay, so for this next question, which is the last question that we wanted to share with you guys on so, oh, and then by the way, this is the figure 13, 14. So I guess I'll quickly go over this real quick, what's kind of going on here, so you can better understand the problem. So again, so this is a logarithmic plot showing viscosity versus temperature of the borosilicate glass, fused silica, high silica, and soda lime glasses. So you have the melting point, which corresponds to the temperature at which the viscosity is about 10 pascals per second. So basically they're talking about this line. It was dotted, but I just wrote over it to black. And then the working point represents the temperature at which the viscosity is 10 to the third pascals per second. Or we just say 10 to the fourth pascals. And in this region, which is showing here the working range, the glass is easily deformed at that viscosity. And then the next point that they mention here is the softening point, where the temperature at which the viscosity is 4 times 10 to the 6 pascals per second, or 4 times 10 to the 7 pascals. So up here at this point, so above the working range. And this is the max temperature that which a glass piece can be handled without causing significant dimensional alterations. And then if we go a little bit higher than that, we'll see an annealing point, which I believe is related to this problem in particular. That's at around 10 to the 12 pascals per second, and that is just where atomic diffusion is sufficiently rapid to where that any residual stress can be removed within in a very short amount of time, about 15 minutes. So basically, at that point, the glass is melting, and you can work with it as you need to. And then the final point that they mentioned here was the strain point. So the strain point is at about 3 times 10 to the 13 pascals per second. And for temperatures below the strain point, fracture can occur before the onset of icing deformation, and the glass transition temperature will be above the strain point. So above all this is going to be your TG. So now if we read the problem, it's saying for many viscous materials, the viscosity of, I believe that's U, may be defined in terms of the expression that they give here, which is similar to what we saw earlier that I wrote down for you guys, or in that slide I should say. I think it's the same thing, I'm not too sure, but this is the equation that they give for us to solve this problem in particular. Where sigma and dE dt are respectively the tensile stress and the strain rate. And then they tell us about a cylindrical specimen for a soda wine glass with a diameter of 5 millimeters and a length of 100 millimeters. And they're going to subject it to a tensile force of just 1 newton along its axis. And they want to know if its deformation is to be less than 1 millimeter over a week's time. And using this figure here that we're just kind of moving, they want us to determine the max temperature to which the specimen may be heated. Okay, so for this problem, okay, so they want us to determine the max temperature to which the cylindrical specimen of soda wine glass can be heated in in order, that its deformation is less than 1 millimeter over a week's time. So first thing that we should try to calculate is the stress. And as we know, stress is just the force over the cross-sectional area. And so we know our force is 1 Newton from the problem. And our area is just going to be pi multiplied by 5 times 10 to the negative 3, I should write it here, this is going to be meters divided by 2 squared, and this should just be, so here's just the conversion from millimeters to meters, just keeping everything outside. This equation here is just this, so if you remember this, or the area equation, we're good. So that's essentially what this is. And you will end up with 5.09 times 10 to the 4. I'm just going to write it like a scientific notation. And that would be in pascals. And the dE dt is going to be what looks like the change in deformation over time. And so to figure out what that is over time, given that we know our stress now, it's going to be dE dt is going to, or as you say, it can be represented as this here. It's going to be a change in length over the original length. That's going to be divided by time. So now if we plug all that in, and then in this first part I should mention is from information from here. So they mentioned that the deformation has to be less than a millimeter over a week's time. So now we have 1 millimeter divided by 100 millimeters. I believe they told us 100 millimeters was the overall. Yes, so 100 millimeters was the overall length. That's why we had that there. And then that is divided by, so we can say 1 week, but then we can break this down. So a week is basically 7 days. In a week, there are 24 hours in a day. So basically the DT is trying to help break down we're breaking down the units of weeks into seconds at this point. And then we know that we have 300 or 3,600 seconds per hour. So as you see it, you can just go through and start canceling units. So when you do this multiplication, you end up with units that are, or that have seconds in them. And that calculation should come out to be about 1.653 times 10 to the negative 8 inverse seconds. So we need those two pieces of information in order to now use this equation here. So I'm going to write that down here. So we know our sigma, we know our dE dt now. So essentially if we plug those values in and we divide them, we should end up with a viscosity of the soda lime glass, which is going to be 3.1 times 10 to the 12 pascals per second. And if we look at our table to see where we can find that value, 3.1, it's going to be kind of difficult to see, but So we should be somewhere around here. I'll just use this line. And this is going to be soda lime glass, right? Yes. Soda lime glass is the one in yellow. So from the figure, the temperature at which we hit that viscosity is going to be at about 500 degrees Celsius. So we start from down here, we can draw a line up, and soda lime glass is the yellow one. So we should be like somewhere in that ballpark if we use the graph to help us solve for that problem. So any questions on this one? We just hit time. Yeah, that's all I have for you guys for chapter 13. Besides these problems, I think everything else will be pretty straightforward, but yeah, that's all we have for you guys today. So we'll see you guys next week.